Okay, so let's just start. So I titled this talk Bounded Degree HDXs for the Working Computer Scientist because my goal in this talk is more that we kind of play around with existing constructions and kind of see the lay of the land. We don't want to really, analyze or do any deep math, more, just understand what's out there in case we're interested in working with high-dimensional expanders, so we'll know what to expect. So I'll start with some opening remarks, mostly repeating some stuff from yesterday, just so kind of we'll have a quick recap. Also, I want to introduce some notation. So let's start with simplicial complexes. These are basically hypergraphs X, so that if I have a hyperedge T inside X, then all its subsets are also hyperedges. We sometimes call these subsets faces. We talked a bit about this notation yesterday. Xi for me is going to be all the hyperedges that have size I plus 1. I know this offset is sometimes kind of annoying, but this is kind of coming from geometry and topology, where we really think of these things as simplices. So like sets of I plus 1 points often have dimension I. So in particular, x0 is going to be the vertices, x1 is going to be the edges, and so on and so on. And the dimension of the simplicial complex is just going to be the maximal d so that xd is not empty. So in a d-dimensional simplicial complex, the maximal set size is like d plus 1. Okay, this is not super important, but like all the complexes we've seen so far and all the complexes today are going to be pure, which means that like a d-dimensional simplicial complex, all maximal faces have size d plus 1. The most important definition from yesterday is the definition of a link. So basically a link is like our high-dimensional generalization of a neighborhood in a graph. So formally, a link of some face S is obtained by taking all the faces T that contain S and then removing S from them. And I like to actually visualize this pictorially. So suppose we have this simplicial complex with 4 triangles and all the edges inside the triangles and all these vertices. And suppose we look at the singleton B or the vertex B, and we see that its neighborhood is, these 2 disjoint edges, because if we have this triangle ABC, once we remove B, we get an edge, or if we have the edge BD, once we remove B, we get the vertex D. And so this is kind of how we view links, also in this more graphical way. And I'll also remind you the definition of a high-dimensional expander. We say that X is a lambda HDX if, first of all, the base graph, only consisting of vertices and edges in X, is a lambda expander graph. And the base graph of every link in X is also a lambda expander graph. Of course, when I say every link, I mean every link which actually has vertices and edges, right? Like top-dimensional faces, the link is empty. So for example, in a 2-dimensional simplicial complex with vertices, edges, and triangles, we'd like the base graph to be an expander and the links of vertices to be expanders. Also here, maybe I'll just remind you, when I say a lambda expander, we mean a lambda one-sided spectral expander. All the eigenvalues except the trivial ones are bounded from above by lambda. And as Max told us yesterday, this is kind of a measure of like very robust connectivity of these respective graphs. Great, so this is my recap, just maybe to say what is a bounded degree complex, because today we'll focus mostly on bounded degree high-dimensional expanders. So for me, the definition of a degree is just going to be that the degree of a vertex is the number of vertices adjacent to it, the number of vertices in its link, or equivalently, the number of edges connected to it. This is slightly different than the definition that Max gave yesterday. And a family of simplicial complexes is bounded degree if we can find a single number m, so that for every vertex in every simplicial complex on the family, the degree is at most m. And let me just comment that if you still like the definition that Max gave yesterday, that the degree is not just the number of adjacent vertices, but the number of total faces containing the vertex, Once we have this bound M, we also have a bound on like the total size of the link or the number of faces that contain a vertex. So if we kind of don't really care about what this M is, as long as it exists and it is finite, then we also get a bound. Of course, you can also ask fine-grained questions. I mainly chose this definition of a degree because it's kind of easier to count. Good. Next question, why do we even care about bounded degree construction, right? I mean, the definition of HDXs doesn't say anything about bounded degreeness. And here I kind of want to draw the analogy to expander graphs, right? So expander graphs are this like extremely useful tool in many areas of theoretical computer science. And there too, we don't really need them to be sparse or bounded degree, but often in the more, I don't know, exciting applications, the kind of degree or the sparsity really corresponds to some kind of cost of using this expander graph. So either, the more bounded degree, the more de-randomized our object will be, or the more succinct our object will be, or something like that. And so these things are often at odds with each other. And so high-dimensional expanders, which are also supposed to be kind of sparser models of the complete complex, often we really enjoy this sparsity in like other properties of our complexes. So let me just also flash some applications of bounded degree or at least non-trivially sparse HDXs. So Mitali told us yesterday about these short high error PCP constructions coming from HDXs. There are also HDXs that are used to kind of de-randomize interesting property tests like agreement tests, constructing interesting error correcting codes, and even constructing other expander primitives, such as the lossless expanders that Rachel just told us about. And finally, maybe let me just say that like high-dimensional expanders that are bounded degree are like notoriously hard to construct. So maybe to continue my analogy to expander graphs, nowadays we know to many constructions of like bounded degree expander graphs. So this is kind of a well-understood problem. So we have constructions coming from algebra, so like, I don't know, Cayley graphs and such. But we also have like very simple random models to sample bounded degree expander graphs from, or even like very elementary algorithms like the zigzag product, where you kind of feed the algorithm a small expander graph and it kind of grows it into a larger and larger family of expanders in a way that doesn't require any like sophisticated algebra or something. However, constructing bounded degree high-dimensional expanders seems more difficult, not computationally hard, but mathematically complicated. And in particular, only the algebraic methods kind of generalize well to higher dimensions. So even dimension 2, only complexes with triangles, we only know how to construct these bounded degree objects using some kind of algebra. And so let me just throw this out here. In fact, this is a pair of open questions. First of all, do we have a more elementary or algebra-free construction of bounded degree HDXs? And second, can we, find some kind of random model to sample bounded degree HDXs from? So there's like quite a big body of work on these two questions, but the way I phrased it, it's still open. So if you're looking for like a nice combinatorial question, this is like a good thing to think about. Good. So what are we going to do in the next, say, 40 minutes? So we'll actually talk about 3 families of HDXs in this talk. We'll start with the spherical buildings. This is like a very simple and elegant construction. It's not going to be bounded degree, but I still want to present it as kind of a warm-up. And also, these are like the first maybe non-trivial HDXs that are out there. So often, if you want to think about some, I don't know, property that HDXs may or may not possess, this is like the first place I tested on. After spherical buildings, we'll talk about a family of bounded degree HDXs that are called quotients of the Bruhat-Tits buildings. So these sometimes are mistakenly called Ramanujan complexes. And though we won't be able to like describe them in full because it requires some non-trivial mathematical language that we probably don't have, what's nice about them is that their links will actually look like the spherical buildings we already described. So at least we'll get some like good local understanding of them. And after we finish with that, we'll describe a third family of bounded degree HDXs, which actually we will be able to describe in full because they're much more elementary. So let's jump right in. So spherical buildings. I'm not going to describe what a spherical building in general is. I'm going to describe only a particular type. They're called sometimes type A, but they're by far the most popular spherical buildings in our community. So let's just define them. So a spherical building is defined using two parameters, q, which is some prime power, and d, which is some integer greater than 1. And we'll denote them S or SQD when we need to emphasize the parameters. And these will be d minus 1 dimensional complexes that we'll define like this. So the vertices are going to be linear subspaces. So let's recall that because q is a prime power, we have a unique field of size q. So we look at the vector space fq to the d plus 1. And for every linear subspace in it, we just put a vertex in our complex. Except, of course, all the space and the zero space, we don't put vertices for those. And now edges, or in particular faces, are going to be according to these chains of containment. So an edge is going to be just a pair of subspaces where one is contained in the other, up to some reordering. And similarly, for higher dimensional faces, triangles are going to be these triples so that we can order them such as one is contained in the next and is contained in the next. And similarly, for higher dimensional faces. So these are spherical buildings of type A, but let's maybe do some examples so that we'll get more of a feel of these complexes. So let's start with d equals 2. And also, at least in my drawings, I also took q to be 2, just so that we'll have not too many vertices, but the picture will kind of stay the same for any field size. So for d equals 2, what are we looking at? So the vertices in this simplicial complex are just going to be lines and planes in f2 to the 3. And here we'll only have edges. So edges will be pairs of a line and a plane, so that a line is contained in the plane. So you can see that this is, or maybe you can't, but this is like a 3 regular graph in this case. So, we don't have triangles yet, so this is just a graph. But still, this is a very classical graph. I think it appears a lot in PCP literature, low degree testing. So it's nice that it's also part of our family. In particular, this is a decent expander. Its expansion is something like 1 over square root q plus 1. So here it's like 1 over square root 3. And in general, as we take the field to be larger, it's a better and better expander. Okay, so this is nice, but not a real high dimensional object yet. So let's take d to be 1 larger. Now, our vertex set will be lines, planes, and hyperplanes, or 3-dimensional spaces, and f2 to the 4. So already there is some imbalance. You see there are many more planes than lines or 3-dimensional spaces. And, as per our definition, triangles, say, are all these triples of line, plane, and 3-dimensional space, that where one is contained in the other, is contained in the other, and of course, likewise for the edges. So if you just look at the base graph of this thing, like vertices and edges, this is maybe slightly less classical, but this is still a 1 over square root q plus 1 expander. And I mean, I won't do this today, but kind of, how do I? Oh, yeah, kind of, if you look at, the bipartite graph between any two kind of respective parts, this kind of looks like, a lines versus planes or lines versus 3-dimensional space or something like that. So, I mean, you can probably convince yourself that this should also be a good expander if you believed me about the lines versus planes. But okay, probably the next question that we should answer is, this is already a simplicial complex. How do links look like? Do links expand here? So let's look at these things case by case. So what is a link of a 3-dimensional subspace here? So let's fix some 3-dimensional subspace R0. And kind of look at its link. So I hope this picture is familiar. So what are the vertices in the link? Right, who is connected by an edge to some R0? It's just all the spaces contained inside R0. So lines and planes, and as this is a 3-dimensional space, inside F2, at least in the picture, we see that we have 7 lines and 7 planes. So what about edges? Do we have edges in the link? Well, yes. So a pair of a line and plane will be an edge if and only if the line is inside the plane. And this is just follows. This just follows from like definition chasing, right? Because an edge in the link is the same as a triangle together with R naught, and because any pair of L and P are already contained in R naught, this will be a triangle if and only if L is inside P. So there we go. We have another copy of the lines versus planes graph, or the spherical building of one dimension less. So already this is some nice recursive structure arising here. So at least the link of a 3-dimensional subspace is a good expander, at least if the field is large enough. Good. What about 2-dimensional subspaces? Well, so links here will look slightly different. So let's fix our 2-dimensional subspace P naught. This time, vertices will have 2 different flavors, either lines inside the plane or 3-dimensional subspaces that contain the plane. And this time, if you think for a second, what edges do we have in the link of a plane? Well, we'll have all pairs of line in 3-dimensional space, because like for every line contained in the plane and every 3-dimensional space that contains the plane, we will always get this like chain of containment. So in other words, this is just a complete bipartite graph. Those of you who have maybe listened carefully to Jonathan's talk yesterday, these spherical buildings are also an example of path complexes, and somehow these complete bipartite graphs are exactly what you get in certain links of path complexes. So, and even if not, at the very least, we have here a complete bipartite graph, so we know that this is an excellent expander, like even better than 1 over square root q plus 1. This is just like a 0 one-sided expander. Good. So let's go quickly over the third case. What about the link of a line? So for L naught, the vertices are planes in 3-dimensional spaces that contain this line. And edges are just pairs of plane in 3-dimensional space where one contains the other. And kind of, if you know something about quotient spaces, then this shouldn't surprise you that this is also a copy of a lines versus planes graph. So this is not too hard to show. I don't want to go over it, but in any case, somehow links of lines also have this nice recursive structure to them. So we see like a spherical building of dimension 1 less here. And in particular, this is also a 1 over square root q plus 1 expander. So maybe just somehow to conclude, if we look at d equals 3, we saw kind of by hand that all the links and the base graphs are a 1 over square root q plus 1 expander. And so this is like a high dimensional expander that we kind of spelled out explicitly. So now let's like unset D and talk about properties in general of these spherical buildings. So first thing you can ask, like how many vertices actually are there? And this is just some kind of subspace counting. You get roughly something like q to the d squared over 4. And what's the maximal degree? Well, I promised that this is an unbounded family of simplicial complexes. So the maximal degree is like q to the d minus 1 squared over 4. And like one reason for this is that if you look at subspaces of like dimension d, then their link will actually look like a spherical building of like 1 dimension less. So we expect this degree from them. And of course, it doesn't matter if we take q or d or both of them to infinity, the degree is unbounded. So we're not going to get a bounded degree family from this. Expansion in general in d dimension is going to look like this 1 over square root q plus 1, so only dependent on the field size. And let me just say that there is some kind of nice recursive structure even for higher d's. So like faces of dimension d minus 3 or size d minus 2, their link will either look like a complete bipartite graph or some kind of lines versus planes graph. And even for links of smaller faces, we will still see something that looks like a combination of maybe a complete graph and some kind of spherical building. There are also formulas for like how an arbitrary link looks like. They're slightly less elegant, but still links are very structured. So this is also something that's nice in the spherical building. So this is basically all I wanted to say about spherical buildings. Maybe this is a good place to pause for questions if there are any. Yeah. Yeah, so as I defined this, you only look at linear subspaces. You can look at affine subspaces, and this is still interesting. I think this is also an HDX. I'll say, you can do many variants of these things. For example, you can also maybe only take linear subspaces of certain dimensions. This will also often give you like a slightly better degree trade-off, although still not bounded degree. But yeah, I mean, this is a very natural thing to do also for affine subspaces. Yeah.
I understand that the trade-offs between degree and size of the graph, so it seems like you save roughly a factor of 2 to the d between compared to
Yeah, roughly something like that. I mean, I like to think of d as kind of fixed, right? And now, the degree here is some polynomial.
It's like an n is like an n to the 0.1 degree kind of graph.
Maybe n to the 0.9, but yeah. I mean, right, because d is equal 100, so you have like 100 here and 99 here, but yeah. Okay, awesome. So now I want to talk about quotients of the Bruhat-Tits building, but maybe let's talk for a second about the Bruhat-Tits building itself. So the affine Bruhat-Tits building, or sometimes just the affine building, or specifically today we're going to talk about affine buildings of type A tilde. There are more, but this is kind of the most well-known. I'm not going to define this structure formally, but it's also parameterized by some prime q and some integer d. And this is basically a d-dimensional infinite simplicial complex. We'll denote it bt. Okay, and even though I'm not going to explicitly define this infinite simplicial complex, the main thing that we kind of need to know about it is that for every vertex in this Bruhat-Tits building, the link of the vertex looks like the spherical building that we just described with the same parameters q and d. So a link of a vertex here is not only finite, it's very familiar, it's these spherical buildings. So, as an infinite simplicial complex, we don't really know how to define maybe high dimensional expansion on it because we don't have like a finite base graph to it, but at least all the links are high dimensional expanders. So maybe almost a high dimensional expander for us. And before I say how we can construct families of bounded degree simplicial complexes from this one infinite complex, let me just say, as an historical note, that this building was, it was well known from the 50s, studied by Bruhat and Tits, but studied for, its quotients were maybe studied for generalizing some notion of Ramanujan graphs to Ramanujan complexes. And this is why, for a very long time, all quotients of the building were sometimes called in the literature Ramanujan complexes, even though this is not very accurate. So this is something that people have been doing even before the definition of HDXs since early 2000, I think. And so kind of the standard way that you take some infinite object and create finite objects from it is maybe called quotienting. And very informally, to take a quotient of this infinite object is basically just to glue a lot of vertices together so that it kind of folds on itself and you get a finite object. I want to describe this slightly more formally, but this maybe requires some more background in group theory. So if you don't, you can space out for the next slide and we'll do something else in a minute. But formally, one nice thing about this Bruhat-Tits building is it has a very rich set of automorphisms. So to quotient it, you need to take some subgroup of automorphisms that act on this building, and you quotient using orbits. So an orbit of a vertex in the Bruhat-Tits building is just all the vertices that you get if you apply some automorphism from the group of automorphisms that acts on it. And so the quotient complex, which I denote BT divided by G, is just a simplicial complex whose vertices are orbits. So we're folding all vertices in an orbit to a single vertex. And faces are going to be obtained by taking some face in the infinite object and looking at all its orbits. Okay, so all the orbits of the vertices. So, I mean, this is like the formal definition of a quotient. And now you should ask yourself like a million questions. Like, when is this object finite? Why, if I start from an I face here, things don't collapse? How does this object look like? I mean, these are all good questions. And I'm not going to answer them today. And like one other fact that's not entirely trivial, and like I don't expect you to really understand this on your own, is that if you look at the finite object and you look at the link of an orbit, it's going to be isomorphic to a link of any of the vertices inside the orbit, so in the infinite object. And in particular, because of the structure of the Bruhat-Tits building, an orbit here, its link will also look like the spherical building. Okay, so under like very mild conditions on G, we will get like this nice finite object where a link of every orbit is going to look like a spherical building. And so to construct families of bounded degree HDXs, we really take, this one Bruhat-Tits building parameterized by some Q and D, find different groups, G1, 2, 3, that act on this building, and just take quotient complexes with respect to these different groups. And we'll get like finite simplicial complexes that are connected. The link size will be q to the d squared over 4, but this time q and d are fixed, so this is not growing in degree. This degree is constant. You maybe need to use the trickle-down theorem from yesterday, but because all links are very good expanders and the underlying graph will be finite and connected, then we will also get that the base graph is an expander, or that all these xi's are HDXs. Maybe you lose something slightly, but still roughly a 1 over square root q HDX. So again, I just want to emphasize, yeah. You ask what's the point. So if you take one group, right, you get one simplicial complex. It's finite and everything. If you want, more and more groups, you get more like a family of simplicial complexes, right? Because we don't want just one. For any application, we probably want, to tailor the number of vertices to, yeah. So I just want to kind of re-emphasize that I haven't really told you, how the building is constructed, how these groups look like, what, the resulting complexes look like, but still kind of this local property where links look like spherical buildings, you can often get a lot of mileage from it. And in many applications, really, this is kind of the only thing that people care about. And so often is the case that if you hear about like a Ramanujan complex or a quotient of the building, this is the only thing you should say to yourself. Oh, it's like a finite complex. Links look like these vector spaces, lines versus planes, and so on. Good. So any further questions about this? Where? Oh, yeah. Right. And by the way, this is sort of by design. Like there are a lot of theorems, I'm not sure if specifically for the building or not, that kind of show that if you take quotients of an infinite object, at least spectrally, you're supposed to kind of converge to like the spectrum of the infinite object. And so, for example, like the Alon-Bopana bound, which is like this classical bound on like the trade-off between expansion and degree in like graphs. One way to at least prove it is to say that like you have some version of like an adjacency operator on the infinite tree, and all degree D expander graphs are quotients of it, and therefore they can't at least asymptotically improve on what's happening on the tree. And so here it's the same thing. So our goal is not to improve anything. It's really just to create a finite object that kind of approximates or emulates the infinite object locally. Yeah, I mean, okay, local spectral information, we're not like, we have the exact same link, so we're not gaining or not losing anything. If you look at like expansion of the base graph or something like that, then I think some version of an alone Bufana bound should hold also for these objects, although I'm not sure if somebody ever did this or not. There is, maybe Amitai Kamber did it, I don't know. Yeah. Yeah, okay, good. Like, it's good that you're asking me these questions, but I'm far from an expert on these buildings, so take everything I say with some grain of salt. Um, okay, and now for something completely different. Our final family of coset complexes. So again, maybe just a historical note. Coset complexes are actually complexes that were constructed and known, I think, since the 50s. But they were introduced only in 2018 to our HDX community by Kaufman and Oppenheim that really observed that some coset complexes should also be high-dimensional expanders according to this like local spectral expansion definition. And later on, other people kind of analyzed more variants of these and showed that in general, this is like a good paradigm to construct HDXs. And as I said before, they're based on more elementary group theory, so we will be able to describe in full at least one of these. In this talk, I'm going to show only a two-dimensional simplicial complex, so vertices, edges, and triangles. This is just mainly for ease of notation, but the generalization to arbitrary d-dimension is rather straightforward. So maybe kind of before like describing these things, I'll give you some kind of high-level idea. So these complexes are described as follows. We'll have some ambient set of points, which are not going to be the vertices of our simplicial complex. And what we're going to do is we're going to partition these points in several ways. And our vertices are going to be parts in a partition. So for example, maybe I have like, I partition these points in like this way. So I'll add 4 vertices to my simplicial complex. Then I did another partition, and I'll add maybe 5 more vertices, 1 for each part in the complex, and so on. And now I need to tell you, how I put edges and triangles. And so I'll put faces on sets of partitions whose intersection is not empty. So I don't know, I can like lay over the partitions one on the other. And for example, I see that, I don't know, P1, R1, and Q3 contain a point in their intersection. And so I'll put a triangle on there. So maybe just to repeat this kind of a bit more formally, we're going to take 3 different partitions of some set G. The vertices are going to be the parts in each partition. The edges are going to be 2 parts in different partitions that intersect non-emptily. And similarly, triangles are going to be sets of 3 that whose 3-wise intersection is not empty. And how are we going to find like such a nice partition that will give us like HDX properties? Maybe this shouldn't surprise you. G is not just going to be some set. It's going to be a group of 3x3 matrices, a special linear group. And these partitions are going to come from cosets of certain subgroups. So let's say who G is. So the group or the set partitioned, it's going to be matrices parameterized by 2 parameters, some integer m, and again, a prime power, which we'll use for a field. The entries on these matrices will just be from some ring of polynomials. So think of matrices of degree at most m, but if I kind of multiply 2 polynomials and I get something of degree larger than m, I kind of truncate at m. I only take like the degree m part. And our group G is just going to be 3x3 matrices with entries, these polynomials, with determinant 1. So the special linear group over these matrices. Okay, so it's just some group. And now you can ask kind of what are the subgroups that I'm going to use. So let me just put them here on the slide. So yeah, I mean, I can just, describe them. So for example, H1 is these upper triangular matrices with ones at the diagonal, two polynomials of degree at most one, so linear polynomials above the diagonal, and a single quadratic polynomial two above the diagonal. And H2 and H3, they also have a similar description up to some kind of shift in rows and in columns. And I kind of want you to already observe that even though G, right, it has like matrices with polynomials of degree m, which can be, I don't know, very large. These H's, right, they don't depend on m, right? Every matrix here is defined by like two linear polynomials and a quadratic. So it's kind of the same groups for like different sets G. Good. So our partition, we're going to use left cosets. So just to remind you, a left coset G times HI is just taking all the elements in HI and like multiplying them on the left from G, and this forms our partition. So like, I'm not sure if this is a very helpful example, but if we have this matrix, then its left coset is going to look kind of like H1 here, but with minuses on the sum of the diagonal. So in any case, our coset complex, X or X parameterized with M and Q, the vertices are just going to be the cosets in the three partitions. Edges are going to be two cosets that intersect non-emptily, and similarly, triangles are going to be three cosets that intersect non-emptily. Of course, if we want higher dimensions, we need to take maybe 4 subgroups and like maybe enlarge our matrices a little, but the definition, I think, is kind of clear. So up until now, I mean, maybe I'll leave this definition for like another 10 seconds and just say, I mean, this is like a very formal definition, right? And like I didn't even need to specify the group to like show you this slide, but kind of I want us to play around with these complexes too, to kind of like get a better understanding of what we can expect from them. So let's kind of think about some basic properties. First of all, how many vertices are in such a complex? So the number of vertices, right, is just like the number of parts in the three partitions. Every coset has the same size, the size of the group HI, and so the number of parts is like the size of G divided by the size of every H. And every H, again, these groups don't get larger and larger as M grows larger. There's something like Q to the 7th. And but the size of G does grow as we take polynomials of higher and higher degree. So we'll get size that's something like Q to the M, maybe some constant before this M. And kind of I want you to observe that this grows exponential with the maximal degree of polynomials, okay, not degree of the vertex, the degree of polynomials that we allow ourselves in G. So kind of if we keep Q constant and just let M grow, right, we still get a family of complexes with a growing number of vertices. So what about degree? So to tell you about the degree, let's talk about the neighbor set of a coset. So let's look for concreteness on cosets of H1. I claim that their neighborhood consists of cosets that look like the same G times some element H inside H1, which are cosets of either H2 or H3. And this is kind of following almost immediately from the definition, because if we have some element inside the intersection of GH1 and G prime, say H2, then just because it's in H1, I can write this element as like some G times some little h in H1. And so this G prime is also this coset of X or the coset of GH2. And this already gives me a good bound on the degree, right? Because I can specify an element in the neighborhood just by giving you an element in H1 and, telling you if it's a coset of H2 or H3. So already we get this like bound, which is some like small polynomial in Q. The actual number is actually lower because there is some double counting here because different elements inside H1 can give you the same neighbor. But this is, I mean, slightly non-trivial. We won't, maybe we'll see why this is in a few slides. Let me just comment that for higher dimensions, the degree grows also something like Q to the D squared. So like even in higher dimensions, if you fix both Q and D, you will get something that's constant in degree, and you can like take the maximal polynomial degree M to grow to infinity to get like an infinite family of bounded degree complexes. Another nice corollary of this like this nice formula for neighbors is that this gives us like a very simple or structured routing algorithm to construct paths between pairs of vertices inside these simplicial complexes. So imagine we want to take a path from like GH1 to G prime H1. What we really do is we kind of write G inverse time G prime as like a product of matrices where every matrix is inside the subgroup. And then we kind of traverse from the coset of G to the coset of GH1 to the coset of GH1 H2 up until we get to like a coset of G times this product, which is going to be G prime. So if you haven't followed me in this like last sentence, it was maybe a mouthful. If, for example, G inverse G prime is equal to this H1, H2, H3, where every little h is in the corresponding capital H, then like we just go from GH1 to G times little h1, which is a coset of H2. And then we use the fact that little h2 is inside this coset to go to GH1, H2 times the coset H3. And then we do this again to arrive at G prime H1. And maybe this is not like the most general case, but like for any two vertices, we can route in this similar way. So kind of finding paths here is basically like writing matrices as products of matrices in the group. And let me just say for a fact, okay, that for any matrix G, we can always find a bunch of matrices in the group whose product give you G. And so in particular, this complex is connected because from any two vertices, we can like find a path in this way. So good. We have a complex, it's bounded degree, it's connected. So is it a high dimensional expander? So again, kind of to show that X is a high dimensional expander, this is like a very common strategy. We just need to show that, you know, its vertex links are expanders. And then kind of by the trickle down theorem that we saw yesterday, we'll also get that the base graph is, you know, almost as good as an expander. And so this will also be an HDX. So maybe this is a good time to talk about how links look like. So how does a link of a coset look like? Okay, so the first thing that we kind of observe is that all links of cosets of the same subgroup should look the same. I only took here H1 kind of to be concrete, but H2 and H3 have a similar analysis. So all links of cosets of H1 will look the same as the link of, you know, the coset of the identity of H1. And kind of to see this, we need to observe that this complex is very symmetric in the sense that we always have an isomorphism of the simplicial complex that will send GH1 to H1. And this isomorphism just sends some coset XHI to G inverse X HI. And you can kind of, you know, follow the definition to see that this is indeed an isomorphism of simplicial complexes. You know, triangles get sent to triangles and the same in reverse. And so as GH1 gets sent to H1, their links have to look the same. So we don't need to analyze, you know, all the links for every single coset. We really only need to look at three cases, the cosets of H1, H2, and H3. So let's just look at the link of H1. So here, one other nice property that we have is that links of coset complexes are also coset complexes of dimension one less, or in this case, you know, a coset graph. So the group that we're now partitioning is not all G, it will just be this H1. And the partitioning subgroups that we will use are the intersections of H1 and H2 and H1 and H3. I'll call them H12 and H13. And, you know, they also have like very explicit descriptions, as you can see here. And so XH1 is actually the coset graph defined by, you know, these two partitions according to H12 and H13, and, you know, edges according to non-empty intersections. This is, of course, also something that's, you know, maybe too abstract to actually, you know, gain some knowledge from, at least if you don't know something additional on these subgroups. So I also want to give some alternative and very elementary description of this link, such that you can at least hope to understand how you can get expansion from it. So Harsha and Saftarishi observed that you can also look at this link and show that it is isomorphic to a very simple bipartite graph, where in each part you have vertices that are like pairs of a linear and quadratic polynomial, and you connect two vertices on each side if the product of the linear parts is equal to the difference of the quadratic parts. So again, we're not going to get into why this thing is an expander, but at least maybe you can get a sense of like, you can probably analyze this graph using some kind of standard expander theory tools. So Kaufman and Oppenheim showed in their work that this is like a 1/√Q expander. And later on, Harsha and Saftarishi gave like a more elementary analysis that doesn't use tools from property T theory, just like this kind of description. And I also mentioned here O'Donnell and Pratt that gave like a third elementary analysis in their paper, which I encourage you also to check out, because you can also kind of generalize their analysis to other complexes as well. So maybe just to conclude on this family, so by the trickle-down theorem and these links, we get that these are HDXs. And so for any expansion lambda we want, and any dimension D, we can kind of take our field size to grow proportionally to 1/λ², and take M just to grow, and we'll get like a family of HDXs that are like lambda expanders and have this like degree, which is constant if we kind of fix Q and D. Great. So I have like one more slide here. Up until now, we kind of saw all these basic constructions, and I hope you got more of a feeling of them. I just wanted to kind of briefly say what else people are doing when they're thinking about HDX constructions. So I already mentioned that we're kind of looking for more algebra-free constructions. But also, people are working on these constructions to kind of, not only have them, have this like local spectral expansion property, but sometimes we also want, other properties like complexes that like look regular, all links of a certain dimension have the exact same structure, or maybe complexes that have like different notions of expansion, such as co-boundary expansion that Mitali is going to tell us a bit about tomorrow, or like these Ramanujan complexes, which is maybe a third more sophisticated notion of like high dimensional expansion. And also, as Rachel discussed in her previous talk, sometimes, even like simplicial complexes are not the best tool for every application. So kind of we are looking for, other types of complexes or higher dimensional structures, such as these like cubical complexes that Rachel told us about that are also very important in like quantum LDPCs and locally testable codes that Chinmay will tell us maybe in the next session, and also more like high dimensional expanders that maybe take advantage of more of a vector space structure. And there are some more examples out there. So I think maybe I'll stop here. So thank you everybody for listening. Yeah, so any questions? Okay, thank you. Oh, yeah.
Have other fancier notions of dimensional, which of these constructions rather have the fancier notions?
Yeah. Okay, that's a good question. So for co-boundary expansion, like some of you can look at both these coset complexes and the quotient of the building. Some of them will have this property and some won't. Like, so the spherical, yes, actually the spherical thing always has, like there you can always get co-boundary expansion, at least if the like field is not too small, but like Even for like large constants, this is true. But like to get co-boundary expanders out that are bounded degree, you kind of also need to control something about like the cohomology of these complexes. So kind of there it already kind of depends more on the exact parameters. You can't just take like any group and quotient or something like that. You need to do something more. As for Ramanujan complexes, also like this is not something that follows like from just being an HDX. You need to kind of tweak the constructions to have this. Yeah. Okay. Thank you everybody for coming to this session. See you again Thursday. Yes, Thursday.